All right, so we are beginning homework 3 for process dynamics and controls. We're gonna go ahead and I'm gonna kind of go do a brief summary of what we're gonna kind of get into today. I'm gonna draw out our distillation column along with our equilibrium stages. And then we'll go ahead and we'll derive some expressions that kind of correlate to this, that correlate to our liquid and vapor flow rates, as well as our holdups, which essentially again correlate to our rectifying and stripping and kind of how that kind of comes together. But let's go ahead and read this description so we can kind of see what we're getting into today. We will be deriving the differential equations governing the rate of change of liquid molar holdup. So holdup is going to be kind of one of the expressions that's going to be related to our W term that I'm going to kind of initialize in a little bit. And mole fraction, which will be denoted as xn as well, and of the more volatile component in a distillation column. I will assume constant molar flow rates in each section. This includes the rectifying and stripping stages, negligible vapor dynamics, and a vapor flow to the condenser that is perfectly controlled to match the sum of the reflux and distillate flow. The liquid flow rates can be assumed to follow the L equals W times holdup minus holdup 0 to the 1.5. I'm going to show you how kind of that equation comes to be, where holdup 0 is the holdup at which no liquid overflows the weir on each stage. So I'm going to show how the kind of that how that weir kind of relates to our second stage, and kind of how when our water overflows over this certain height, kind of this blockade, kind of how it goes over. I'll draw that out in just a second. But yeah, so this ignores the typical considerate bubble volume and train in the liquid. All right, so let's go ahead and start by drawing out our equilibrium stages. And go ahead and draw these. We've drawn this plenty of times, so don't plan to make it look pretty. 0, 1, 2, 3, 4. Just go ahead and naming these. We know we have our condenser up here. I'm not going to label this, but XD, molar composition of our distillate as well as our distillate. And here we have molar composition of our bottoms as well as our bottoms. And we're going to kind of want to denote our vapors and our liquids a certain way. We also do know we have our feed here as well as the composition of our feed. We also have so let's denote our vapors. Let's start up here. So we have our vapor here. We'll just denote that as V, and then this will be V1. And coming down here will be L naught, liquid. Our initial liquid coming down, and then our liquid here, and then we can also just have our V bars coming up and our liquid bars coming down. All right, we also have a reboiler here, forgot to mention. Let's just go ahead and label all of these. So we have our reboiler and condenser. Essentially, this is a distillation column. We have our rectifying above this feed. We have our rectifying and we have our stripping below this feed. Okay, so let's go ahead. We know that in the essentially at any stage n, in this stage we have our liquid and we have our vapors and we also have this weir. So I'm going to go ahead and draw this out. And some things that we need to know from this is we kind of have this box right here and we have liquid. All right, so these kind of lines are drawn are just the liquid, and we also have kind of this blockade or height we want to call it, but we pretty much know we can change this height right here, and essentially this liquid from the stage will overflow on the way after it reaches a height greater than the wall, essentially this blockade, and will flow down in the stage that comes after it. So let's go ahead and just have our kind of water coming down here. We have this kind of overflowing. Not the best drawing, but essentially we see what this is essentially working for, what we're kind of using this for. Let's go ahead and rewrite this equation that we saw up here. So we have our liquid equals this W, this term we're kind of bringing in, and this will be multiplied by our hold up minus our hold up not to the 1.5. All right. We can also, I'm going to kind of rewrite these terms to kind of make it easier, as well as when we go and code this into Colab. But I'm going to kind of rewrite these terms. Let's go ahead and use M for this. So we're going to do our W term multiplied by our M minus M naught to the 1.5. Okay. Okay, so looking at this stage two, as you can see here, we essentially have our liquid and we have our vapor. And our liquid is going to be contained in this reservoir, or so you can call it, and it will essentially describe this wear that we have here, right? So what we want to do now is you want to find a general expression in the molar holdup in each stage. So essentially, this is our molar holdup that I denoted as M and M naught, and we want to denote this molar holdup in each stage. Let's go ahead and kind of rewrite these terms so it's more or less kind of defined, but we have Mn, kind of just label this. So this is our molar holdup. And we also have Xn. So this right here is our change in mole fraction of more volatile component, I believe. Let's see our description. This is our change. What is this? Change mole fraction of more, change of liquid molar holdup and mole fraction of more volatile component. So just denote this as mole fraction of more volatile component, mole fraction, and again at any stage n of more volatile component. All right. Okay, so now that we have that labeled, we can stay kind of at any stage n. This rate of change in our liquid is going to be a difference between our liquid and vapor. All right, so we can go ahead and kind of define this by kind of an equation that encompasses this molar holdup of our liquid entering and leaving. So let's go ahead and do that. So we have D, the change of molar holdup dmn over dt. And we kind of want to relate this to our stages up here. As you can see, all these stages right here of our stage N, and whether we're going from our liquid side or vapor side, we know that we're looking at a stage N+1 or N-1. So this is essentially of our liquid entering and leaving that we're starting with for now, but we'll introduce our vapor once we kind of change these expressions, and it'll look a little different, but it's going to be equal to ln minus 1 minus ln plus we'll actually introduce our vapor 2 now. So our vapor at stage N+1 minus our vapor at stage N. Okay. All right, so I'm going to go ahead and I'm going to rewrite these terms. As you can see here, we're going to rewrite this as equals ln minus 1. We'll see why. It's because we're introducing our W term, but as our liquid at stage N-1 minus our liquid at stage N. Rewriting this again, we introduce our W term, right? And we also have our molar holdup. We're going to eventually do a component mole balance. So I'm kind of getting to that step, but Mn minus 1 minus M and naught, right? At any stage N, and we looked at it before at our naught. So you can do that. And then again, this is at 1.5. All right. So we're going to minus this again. Introducing this term again, you get Mn minus M and naught. And then this is to 1.5. Okay. So what we want to do now is we want to finally do our component mole balance. All right, so we can finally do our component mole balance. So this is the change of our liquid molar holdup Mn minus our mole fraction of more volatile component Xn over dt, and this can be equal to we're gonna essentially just be multiplying our molar holdup multiplied by our mole fraction. So this will just look like, it's going to look a little long, but Xn minus 1 multiplied by ln minus 1 minus xn multiplied by ln plus yn plus 1 multiplied by Vn plus 1, and then minus Yn multiplied by Vn. All right, so this is essentially our mole fractions of our liquid and vapor multiplied by our molar holdup. So we also want to expand this essentially by using our what's it called, product rule. So expanding this using product rule, what we'll get from it is xn multiplied by the change of our molar holdup over dt plus mn multiplied by our dxn over dt. Okay, so I can go ahead. This right hand side is kind of essentially stay the same, but for time purposes, we're going to kind of we want to rewrite, we're looking at the left hand side right now. We want to rewrite the left hand side and kind of rearrange it using the product rule. So we're essentially going to substitute our hold up balance to eliminate the term from expression on the left hand side. All right, so let's go ahead and see what this looks like after doing that. We're going to get is our mn multiplied by our change of xn, which is their mole fraction over dt plus xn multiplied by our ln minus 1 minus ln. Okay, again, this is our left-hand side. We're going to want to simplify this again, isolating our dxn term. So doing that, so again, just working on the left-hand side. I know it kind of just looks weird right now, but we're focusing on the left-hand side, okay? All right, so rearranging this, we get dxn. Again, we're isolating this term for dxn, change of mole fraction over our change of time. And this is going to be equal to our liquid at stage n minus 1 over our molar holdup multiplied by our mole fraction at n minus 1 at stage n minus 1 minus our mole fraction at stage n. Okay, and this will be added. Again, now we're working on our vapor. So plus V n plus 1, so our vapor at stage n plus 1 over our molar holdup again, and then this will be multiplied by, again, we're looking at our vapor, so it's y, our vapor at stage n plus 1 minus our vapor at stage n. All right, so essentially this is our final equation. I don't think we have anything else left to do, but we can kind of see how these liquid and vapor flow rates correlate to our distillation column, essentially what's coming up and what's coming down, as well as our stripping and rectifying, and how that wear is kind of introduced, and how that kind of changes our kind of our mole fractions and how we kind of isolate the terms and essentially look what we're solving for. Go ahead and box this. This is our final equation. We can go ahead and use this when we work on our Colab coding.